Size of the slit opening and the diffraction parameter. How much a wave bends or diffracts around an obstacle depends on two things: the size of the aperture or obstacle and the wavelength. A wave bends most around an obstacle when the size of the obstacle is comparable to the wavelength. In some sense, the wave sees the aperture or obstacle better when it's comparable to the wavelength, and therefore changes the shape of the wave front most from its initial form. And it is this change that our eye detects. I'm going to use the water diffraction applet to show this behavior by Ng. So what you're seeing here is that if you compare the wavelength, which at its smallest value, and you compare the obstacle size, or the width, which is very large, you're seeing here that there is a strong shadow region in the back here where the waves do not diffract well behind the barrier. So if I had placed a wave detector behind this obstacle, it wouldn't measure any change in the waves because it's not seeing any of the waves. So this would be the case where the obstacle size A is much bigger than the wavelength. Now I have the opposite case. The wavelength is really long and the obstacle is really small. There is very little change in the wave pattern in the sense that it does not see the obstacle. And what I mean by that, if I had placed a wave detector behind the obstacle, it would measure very little change in the wavefront. Now what you've seen here is that if I compare the wavelength to the obstacle size, they're the same. So for waves that are comparable to the obstacle, one clearly sees that the waves diffract very well behind the obstacle, and a wave detector would easily detect changes in the wavefront behind it. So when we start talking about diffraction, it only makes sense to talk about it when the wavelength and the obstacle size are comparable to each other. So in summary here, if the obstacle is much bigger than the wavelength, there is a strong shadow region where the waves do not diffract well behind the barrier. If the wavelength is much bigger than the obstacle, there is very little change in the wave pattern since it doesn't see the obstacle. If the wavelength and the obstacle size are comparable, one clearly sees that the wave diffracts very well behind the obstacle. So when I look at these three cases, if I have a wave detector behind the obstacle, which one's going to detect something the most? It's the one where the wavelength and the obstacle size are comparable to each other. These two will not detect very much difference, so it won't see it. Example, sound and light diffraction. As this instructor faces the whiteboard and speaks, you are able to hear my voice. Why? My voice reflects from the whiteboard and then interacts with my obstacle head. My big head size is around 20 centimeters. My speaking voice is around 120 hertz, so my voice's wavelength is the velocity divided by the frequency. That velocity is the speed of sound, and I get 3 meters. The diffraction parameter reads that A over lambda is 0.07. This is a very small number, so it tells me that there's small diffraction behind my head. We just saw this with the wave applet. If the wavelength is much bigger than the obstacle size, you don't see it. So in this picture here, you're seeing me standing in front of the whiteboard, and then the waves reflect, and because the waves are so much bigger than my head, there's very little diffraction behind me, and therefore the audience, which is the wave detectors, hear my voice well because the waves essentially just wash right over the obstacle and don't see my head. Instead of sound waves, let's use light waves. Say a flashlight of 600 nanometer light that I shine onto the whiteboard that reflects and then diffracts around my head. What happens? If we compute the diffraction parameter, it reads that A over lambda is about 3 times 10 to the 5. So that's about 300,000 times. In other words, A is much bigger than lambda, but if A is much bigger than lambda, very little diffraction around my head occurs and a strong shadow region pops up. So picture-wise from the applet, we see a strong shadow region here in the back. So if I'm thinking about shining light, the reflected waves doesn't diffract behind my head very well. So therefore, I get this shadow right here, and people in the audience, who are the light detectors now, don't see the light because it doesn't diffract well behind my head. Mathematically, how does the diffraction parameter tell us about the amount of diffraction? First, it only makes sense when lambda is comparable to the obstacle size, to maximize diffraction to be able to see it. The diffraction parameter appears in the path difference equation. So if I have A sine of theta equal to ND lambda, if I solve for sine of theta, I get ND divided by the diffraction parameter. So when I look at this term here, remember this is a sequence in values of n. So if I have a small diffraction parameter, then that means that this number is going to be larger, so the sequence stops faster. That means sine of theta being greater than 1 gets there faster, therefore there's less minimas. If I have a large diffraction parameter, the sequence goes on longer because now it's a smaller number on the right, so therefore I get more minimas. So to understand what I just said here, let's go through some examples with an applet. In this example, I have two situations. The first situation has a wavelength of 600 nanometers, and then I have an opening of 1500 nanometers. And the second situation, I have the same wavelength, but now I've doubled the opening so that A2 is 3000 nanometers. If I calculate the diffraction parameter for both of these, you see that A1 over lambda is 2.5 and A2 over lambda is 5. In other words, this has a smaller diffraction parameter, this has a higher diffraction parameter. And when you just look at these things, this is closer to the wavelength than this guy is. Therefore, case 1 has less diffraction, case 2 has more diffraction. What do I mean by less diffraction? There are less minimas. What do I mean by more diffraction? There are more minimas. So now let's go calculate the number of minimas. So to calculate the number of minimas, I use the sequence of sine of n, where nd is equal to 1, 2, 3. So here I have my sine of n. I got nd divided by the diffraction parameter 2.5, and now I just start putting in the values. So it's got to be 1 over 2.5, 2 over 2.5, 3 over 2.5. And what you're seeing here is that immediately this guy now has sine of theta greater than 1. So that means that ND has to be 2. So I have two minimas to the left and right of the central max. So if I repeat the sequence here for the second case, I see that sine of theta is equal to ND divided by 5. So let's go through that sequence. And you could see immediately that if I do my 1, 2, 3, 4, 5, when I get to here, this is sine of theta equal to 1, which is allowable, but 6 over 5 is greater than 1. That's not allowable. This tells me then that ND is equal to 5. So if I look at the diffraction pattern, you could see here that I have two minimas from the central fringe, so the total number is then going to be 4. And if I look at for ND equal to 5, you could see that I got 5 minimas. In other words, this guy has more diffraction than this one over here. That's what the diffraction parameter is telling us. So here is the diffraction applet by Phys4C here, and what you're seeing here is that I set the wavelength to 600 nanometers, and the aperture size is 1500 nanometers. So what you're seeing here is that as light comes in, I have the central max here, which you could see right here at 0 degrees. But then you look at to the right of that, and I 1, 2 minimas here. And so therefore, that's what I'm visualizing here. So in my picture here, you could see here that I have 1 minima here, 1 minima there. But at the very end, it looks like there's a maxima, but that's later on. But on both sides, I'm getting 2 minimas. So now if I increase this number to 3,000, and you start to look at the number of minimas now, I'm then going to start counting 1, 2, 3, 4, 5. And it's hard to see on the screen here. So just to summarize what the applet is, if I look at the 600 and 1500, case here, you're seeing that I get 1, 2, 1, 2. The ones at the end are not minimas, they're actually maximas. And if you look at this scenario here, we're able to count 5 where the ones at the end are minimas. There is another way to determine ND. The path difference equation reads that sine of theta is equal to ND divided by the diffraction parameter. If we want the maximum value of MD, then maximal means when sine of theta is equal to 1. So ND max is directly proportional to the diffraction parameter times the sine theta max, which is 1, so therefore I get A lambda. Let's go back and revisit the example with the two situations. In that case, we had case 1, which gave us this wavelength and this slit opening. The diffraction parameter was 2.5. In case 2, the diffraction parameter was 5. So if I calculate the maximum value for MD max, in the first case I get 2.5. In the second case I get 5. The question is, what does this all mean? If I look at this, I want to look at ND equal to 1, 2, 3. So if I draw the diffraction pattern, note that I'm only drawing half of it, I got 1, 2, 3. So the question is, where is 2.5 at? The value 2.5 is between 2 and 3, of course, but it's closer to a maxima than a minima. So when you go back and you look at the apt, why was there a maxima for the ND equal to 2.5? It's because the ND value of 2.5 falls right smack in the middle between these two. And if you look at the second case, note that this is a perfect 5. And because it's a perfect 5, it lands on a minima right at the edge. If it wasn't a perfect 5, then I could have part of a maxima. But I don't in this case. And so that's why I have exactly 5 minimas.